This is video number 3 for sample exam 3 for Math107. Here we have a rational function, 1 over x minus 6. Why is it a rational function? Because there's a polynomial here and a polynomial here. Remember, a rational function is of the form p of x over q of x. Alright, for this rational function, what is its vertical asymptote? The vertical asymptote is the value of x that would make the denominator 0. Here's your denominator. What value of x makes x minus 6 equal to 0? Obviously, it's x equal to 6 will do it, and that is your only vertical asymptote. What is the horizontal asymptote? This is the long-term behavior. Remember, this is the value of f that f will sort of coast into in the long range. Okay. To find the vertical asymptote, you look at the degree of the numerator and compare it to the degree of the denominator. What is the degree of the polynomial in the numerator? It's just a constant, so its degree, the degree of p, is 0. What is the degree of the denominator? In this case, the degree of the denominator is 1, because that's the largest exponent on x. You don't write it, but it's there. Right. If the degree of p is greater than the degree or less than the degree of q, well, that's a q, that's a problem. Okay. Because 1 is greater than 0, the horizontal asymptote for f of x is 0. Alright, that looks pretty obscure there. Let me try to erase a little bit here. And maybe I can just point out what is being written here. Right. To find the horizontal asymptote, note the degree of the numerator, that the degree of the numerator is less than the degree of the denominator, because 0 is less than 1. Since 0 is less than 1, the horizontal asymptote is y equals 0. As x goes to plus or minus infinity, that means as x gets bigger and bigger and bigger, or closer and closer to negative infinity, then the function will approach 0. Now, what is the x-axis intercept? The x-axis intercept is the value of x that will make the function 0. Actually, it is the 0 of the numerator, p of x. P of x is 1. Since p of x is 1, it can never be 0. There's no x in it, so it's never 0. So there is no x-intercept. It doesn't exist. To find the y-axis intercept, set x equal to 0. Remember, when any function hits the y-axis, x is 0. When I put x equals 0 in here, I have 1 over 0 minus 6, which is minus 1/6. Now use this information to sketch the graph. So let's write on here what we have. I know the vertical asymptote is x equals 6. Right? The horizontal asymptote is y equals 0. There's no x-intercept. It never crosses the x-axis. It crosses the y-axis at y equals negative 1/6. So you can give yourself some axes here. Label them x and y, or f of x. Okay, the vertical asymptote was at 6. Oh, I need a letter. Okay, it's 6. So right at 6, you draw this horizontal dash line. The function can't cross it, right? And it blows up as it approaches it. But 6 is not part of the domain of that function, but you include it as this dashed line. Now what else do you know? It never crosses the x-axis, so whatever's negative will stay negative, whatever's positive stays positive. So let's say this is minus 1/6. I know it's going to come through here. I know in the long range, so here's the function, it's going to go towards 0. So here's that piece of the function. And as it closer to 6, it has only one choice, and that's to go to minus infinity. It can't cross the x-axis and go to positive infinity. Okay, what happens over here? Well, you can put in a value to see what happens. Let's look at, let's say 16. If x is 16, then I would have 1 over 16 minus 6, which is 1/10. This point is positive, all right, like right here. Now there's no x-axis intercept, so it has to stay positive. I know in the long range, it's going to coast out here down towards the x-axis, towards y equals 0. And as it approaches 6, it either has to go to plus infinity or minus infinity. Because it can't cross the x-axis, there it goes. And that's your sketch. These are the important points. Drawing your axes is important. Putting in this dashed line at the vertical asymptote. Putting in the y-axis intercept. And then sketching the long-range behavior as it goes to, as x gets towards negative infinity, this thing goes to 0. As x goes to positive infinity, the function also goes down towards 0. And then its behavior as it approaches the horizontal asymptote. In the next problem, I give you the polynomial, and I give you two starting points. A value of x where the polynomial is positive, and one where it's negative. I use the subscripts, p for the positive, n for the negative. You can use whatever you want, as long as you keep them straight. And in this case, I walk you through it. So if you carefully do each step, at least you get partial credit for that. I know that some people seem overwhelmed by the bisector method. This is an important method. This is how polynomials are solved. There are other methods, but this is one of the basic ways that polynomials are solved on the computer. And it is important. And all it requires is consistency. It's not too hard. Okay, here is your polynomial. Now, if you remember, the way to do this is you find a value of x where it's positive, a value of x where it's negative. And you know, because a polynomial does not have any jumps in it, that somewhere between the plus and the minus, it had to cross the x-axis, and you're looking for that. In other words, you've trapped the root. So the first thing is, I've given you these two numbers, and you need to verify them. Okay, so first put this value, x equal 1, into the polynomial. So the polynomial evaluated at 1 will be 2 plus 1 minus 1 cubed, okay, which is 2, and that's greater than 0. The polynomial is positive there. Let's look at 2. So I put 2 in the equation, and I've got 2 plus 2, 4, minus 2 cubed. 2 cubed is 8. Okay, so this is minus 4. It's less than 0. That means between 1 and 2. At 1, the polynomial is here. At 2, it's down here. So that polynomial might do different things along here, but somehow it has to cross the x-axis, and that's what we're looking for. So between 1 and 2, we have trapped the root, and that's what that means. It has a 0. Another way for saying a root is to say it's a 0. The polynomial has to cross 0 between 1 and 2, because it has to get from 2 down to minus 4. Now in problem number 23, you need to find the next value of x by averaging the two x values. At this stage, many people, or some people, hopefully not you, but some people average the y's. It says specifically here, average the x's. Okay, the first one was 1, the next one was 2, so you get a new value to try out, and this new value is 1.5. So I'm going to draw a little sketch of what we've done here. Here's the y where the polynomial is graphed. Here's x. Here's very enlarged scale, 1 and 2, not very linear looking. When x was 1, the polynomial had the value 2. When x was 2, it had a value of negative 4. I know that somewhere in here it crosses 0, but I don't know where. So I average those two numbers, and I come up with 1.5. Now the question is, did it hit 0 over here, or did it hit 0 over here? I've got to figure that out. The way to figure that out is to put the 1.5 back into the original equation and multiply through. All right, so I multiply through. Here's the 1.5 being put in the equation, and I come up with 0.125. That's a positive number. So it's the polynomial at this point, I guess I'll leave it red, is sitting right here. Okay, now tell me where the root is. Between here and here, I can't guarantee a root. They're both positive. It could be doing something like this, but not necessarily crossing 0. But between here and here, the polynomial has to cross 0 somewhere in between here. So now this is my new, this was x negative as before, but now here's my x positive. So all I have to do is look between 1.5 and 2 for the root. I can forget about this because I know I can't guarantee there's a root out there. It doesn't look like there is one. And now in 25, it says find the next value of x by averaging again the x's. So we average 1.5 and 2 and get 1.75. Oops. Now I don't know whether the root's trapped between, so I have, okay, let me just do like this. Here was the 2, here was a 1.5, 1.5, and halfway between is a 1.75. Now I don't know, I knew that it was positive here and negative here, but I don't know if it crossed in this region or in this region. I've got to find that out. To find that out, take the 1.75, put it back in the original equation and work through it, and now that was negative. So it's negative here. That means the root's in this region. It's between 1.5 and 1.75, and I can forget about this. Now the idea is just to make a sketch of the progress and sort of estimate where the root is. And we've made little sketches all along. So here's my x, and I'm going to have a greatly enlarged scale. I put the 1 here, and I put the 2 out here. And this is like, right. So I started here, it was 2. At 2, it was -4. So I had a dot here and a dot up here. The next thing I found was 1.5. And 1.5 I found, let me make these dots red. I can kind of see them. All right. At 1.5, it was almost 0. It was sitting right here at 0.125. So then the next average gave me 1.75. See, I'm averaging the x's. I'm going to put that in the equation. I've got a negative number here, which I can't really remember, but I remember that it was negative. And so I know that this polynomial is doing something like this. And you might say the root is there, and that's good enough estimate.